Hi, it's Robin. I've got here the Commodore 64 User's Guide that was included in the box when you bought a Commodore 64. Don't mistake it for the Commodore 64 Programmer's Reference Guide, which has pretty much an identical cover, but it goes into a lot more detail and is a lot thicker as a result. The C64 User's Guide gets some criticism for not being very good, especially compared to the book that was included with its predecessor, the VIC-20. But for this computer nerd in 1984 with my brand new C64, this was an amazing book, full of little programs to type into my computer and learn from, even if some of them did have typos. That was just part of the experience. A quick shout out to YouTube channel Josip Retro Bits, who inspired some of this video with a post he made on his community page on his YouTube channel. This helped me pull together a couple of ideas that I've had floating around. He's mentioned my channel at least a few times in his videos and frequently talks about C64 code. And I think you'll enjoy his videos. And he's just a few subscribers shy of 1,000. We'll be looking at some of his code later in this video. Now, back to the user's guide. Now here, page 53, it actually has an early version of the famous 10 print program that I've talked about seemingly endlessly in previous videos. In this incarnation, it's actually 3 lines of code, including a clear screen in line 10, and lines 20 and 40, I don't know what happened to line 30, contain the familiar print characters string, 205.5 plus random, and the go-to for the loop that generates the maze-like pattern. Now, it's interesting that the one-line versions of this program drop the clear screen, and I suppose that wouldn't be a very interesting-looking program if it cleared the screen every time through the loop, which you might think would be necessary with a one-line version of the program. So this goes to show that sometimes when making one-line versions of programs, you might have to discard certain elements and focus on the real core of the program. But it does make me wonder, would it be possible to make a one-line version of 10 print that starts with a single screen clear? That might be an interesting challenge, but I won't derail things with that right now. Okay, who am I kidding? I gotta try. Okay, let's go to the C64. Okay, so we've got the usual here, print character string, 205.5, plus random 1, and semicolon colon, go to 10. And this just alternates between character 205 and 206, forming that maze-like pattern. How can we keep this one line but add a clear screen that only executes once? Of course, if we were just to try and insert a clear screen, which is like that heart symbol there, and run it, then you're just going to get that, right? Although, that's kind of fun. Okay, well, besides printing that heart symbol, we could also try printing character 147, like so, and that's the character code for clear screen. But of course, that's just going to do the same thing. Well, we can take advantage of the fact that printing a character string 0 prints nothing at all. And we can prove that if I just, in immediate mode, print 1, 2, and then character string 0, and 3, 4, and if I press return, you see that it just prints 1, 2, 3, 4. Printing this character string 0 has no effect. It doesn't print a garbage or even a blank space or anything. So what we can do here is print character string 147 minus B, and this is because the first time you use a variable in BASIC, even if you don't declare it, it gets automatically initialized to 0, and that's reliable. It's not filled with garbage like you might have in a language like C. So the first time through, this is guaranteed to clear the screen, 147 minus 0, of course, is 147. They'll print the regular slash left or right. And then once it's printed one character, all we have to do in here is add an extra, sorry about the line wrap there, B equals 147. And then this will print character 147 minus 147, also known as 0. So there's our program. Let's try running that. And you notice that I'm not clearing the screen manually. There we go. A single clear screen. And now the program is running like normal. I do notice that it's quite a bit slower than before, and this is a bit convoluted. I think we can improve this a little bit more. How about we get rid of one of the character strings, that first one, and instead just adapt this single one, change the 205 into 147 plus B, which will be 0 when you first run the program. And then it'll add the random value from this function, which is from 0 up to 0.999, just less than 1, non-inclusive of 1. And then this will get truncated automatically by the character string function. So basically, this whole term on the first run is going to be 147, maybe up to 147.999. But by the time it gets executed by the character string function, it'll be just 147 no matter what. Okay? That's a simple matter of taking the 205.5 that we normally have in there, subtracting the 147, and we get a value of 58.5. So now all we have to do is set B to 58.5, and then this term will start equaling 205.5, just like before. So let's try that again. There's the new version of the program, and let's try running that. Yep, and it does seem to be running faster to me too. And just because I don't like the line wrap here, let's change this to line 0 and take advantage of the trick. Get rid of the old line 10. List it. So there, now we have a one-line program that fits on one physical line even. And if we run that, there, it's a little bit faster still with those extra small tweaks. All right. Well, that was quite the diversion. Back on topic. Okay, with that diversion out of the way, that makes me wonder if we can try to make one-line versions of any of my other favorite programs from the user's guide. Probably my other favorite program in this book is on page 65, called More Bouncing Balls. So this is one of the most interesting programs in this book, I think, and it really opened my eyes to the basics of animation and game programming back then. Okay, so let's try that program from the user's guide. We'll do the clear home. Could do a character string 147 too. Poke 53280, 7. Okay, that's changing the border color. What is that, to yellow? And the background color. Okay, now we're setting x equals 1 and y equals 1. I assume that's the ball coordinates. Line 40, we're setting dx to 1 and dy to 1. And I believe those would be like a delta x and a delta y. That means how far the ball will move each step. We'll confirm this when we actually run the program. Now we're poking to 1024. Don't mind me if I don't include all the spaces here. It's funny that they included all these blank spaces, all this white space in the program. They don't usually do that. So 1024 plus x plus 40 times y, comma 81. So this is putting character 81 or screen code 81 into this memory location. 1024 is the top left corner of the default C64 screen, and adding in the x and 40 times y. So the y coordinate is multiplied by 40 because there are 40 characters per line. So really what it's doing is start at this corner. Every y value of 1 is equivalent to 40 spaces across. Here is plus 40, plus 80, plus 120, and so on. That's how memory is laid out in horizontal rows starting in the top left corner. It looks like a two-dimensional screen, but really it's laid out in memory in a one-dimensional array, if you want to think of it that way, even though it's rendered as this two-dimensional screen. Okay, so this equation just works out based on the x and the y, the memory location to put that circle screen code into. Line 60 for t equals 1 to 10. Next, and that's just a very short delay loop, just to burn a little bit of time for the sake of the animation. Line 70, poke 1024 plus x plus 40 times y. That's exactly the same as line 50, except now we're going to put character code 32 in, which is a blank space, erasing the ball character. Now we're going to modify x by the delta x, delta just meaning difference essentially, or maybe distance, how far it should move in one step. So now we've moved the character over, and this really is the basics of all two-dimensional, actually even three-dimensional video games. It's just a matter of moving characters step by step, and the whole game is a step-by-step simulation which may 60 times per second, for example, update all the variables, refresh the screen, and so on. Line 90, if x is less than or equal to 0, or x is greater than or equal to 39, then dx equals negative dx. So if it's reaching an x position of 0, which is the left edge of the screen, or 39, which is the right edge of the screen here, then it will negate or flip the x delta, or you could think of it as the x velocity. If it's moving to the right, it's a positive dx is 1. When it hits that border, it will flip and become negative 1, and therefore subtract and move left. 100, y equals y plus dy. So this is exactly the same thing for the y-coordinate of the ball. And if y is less than or equal to 0, or y is greater than or equal to 24, they say if y is less than or equal to 0, or if y is greater than or equal to 24, then dy equals negative dy. So it's exactly the same logic as x, except y, and just this number differs because the C64 screen goes from y equals 0 at the top down 25 rows, and y is 24 down here on the bottom row. From 0 to 24, 25 rows, but since it's 0-based, they're numbered 0 through 24. And line 120, go to 50. And that just jumps back up here and loops again. Now the x and y have been updated, and the collision at the edge of the walls, the bouncing logic has happened. Then we just go back up and draw the ball at its new position. Okay, we'll list that, and we'll run that. Well, that is a really pukey color combo there. But you can see that white ball bouncing around. So yeah, it is like a yellow border, and it's that light green, mint green background. That's really pretty horrific. You gotta wonder if whoever programmed this, maybe they were using like a black and white TV or monitor. Who would choose those color combinations on purpose? Okay, so now that we've seen this program, and what is it, 12 lines of code here? Is it possible to make this a one-liner? Well, it's definitely possible to make it a two-liner, because this is what that Josip Retro Bits post that I mentioned earlier was about. He presented a two-line version of this bouncing ball program, so let's try it out. In his post, he says, "This is the shortest bouncing ball code I could write. Can it be shorter?" and then he gives the listing. Okay, so let's try this. Line 0, dx equals x equals 39. Okay, so I see that he's still using dx to represent the delta x and x, the screen coordinates, but he's getting rid of those if-thens and instead using some Boolean algebra here. If x is equal to 39, this clause will return -1 for true, and otherwise it will return 0. And then subtract x equals 0. So using Boolean logic to test for the right or the left edge of the screen without any if-thens. And then subtracting x is greater than 0, a shift and, that's short for and, a logical and, x is less than 39, and then multiplying that by dx. Okay, so both of these are going to return a -1 if they're true. Either this will return -1, or this will return -1, or neither will. And otherwise, this will be true. X will be between 0 and 39 non-inclusive. And then that would be a -1, which gets inverted. And then that's multiplied by the current dx. So if I understand correctly, that should have the effect of flipping dx every time it reaches column 0 or 39. And dy should be basically the same, except with different constants. dy equals y equals 24 minus y equals 0 minus y is greater than 0 and y is less than 24 times dy. Okay, so in that one line of code, it should have taken all that code that's in line 90 and 110 in the original. And then I guess it's up to line 1 to do everything else. Line 1, x equals x plus dx, y equals y plus dy. So that's just the same as lines 80 and 100 in the original. And then we're going to poke, P-shift-O is the abbreviation, a comma 32. Well, we don't know what a is yet, so actually I think that's going to poke 32 into location 0, which is the input-output register of the 6510 CPU, but, well, presumably that's okay. Doesn't seem ideal, but that's all right. A equals 1024. Okay, and here's the same equation to work out the character position, y times 40 plus x, and then we're going to poke A, which is the screen location now we see, with the circle, and then we're going to G-shift-O, which will do a go to line 0. Since there's no line number specified, it'll just go to line 0. So we see now that A is the screen address, 32 again blanks the spot, then updates the position, and then puts the ball there. On the first iteration, that's not so good, location 0, but like we said, we'll see if it works. And if it does, well, that's all we need for Commodore 64 programming. Does it work? Yes. Ship it. Okay, and we'll just try listing that just so you can see it without the abbreviations. And here we go. We'll run it. Well, there it goes. You can see the ball bouncing. You can notice that he didn't clear the screen, but like I was saying, that's typical when you abbreviate a program. You might get rid of some of that kind of functionality. And the screen colors are not changed, like the border and the background, but that is no loss at all. Those colors are horrible, and I'd rather look at the usual blue here. And like the original, you can see it doesn't actually replace what character was there. It permanently erases the code. Well, not the actual code, but the text of the code as the ball bounces through. And that's okay. That's expected. So that's pretty good. And actually, the ball seems to flicker less here with Josip's version than the original. So that's a plus. And really, the flicker comes from the time between when you poke 32 into the screen location And then when you do the next poke, it's the time between when the ball is erased here, a blank space is put in, and it's poked in back again in its new location. That's what affects the flicker. To reduce flicker, you want to keep this with minimum time. What's actually optimal is using a second variable to store the old location, and then you can just back-to-back do the pokes with the old location blanked and the new location with the circle in it. But that would require an extra variable and an extra assignment, which may be a luxury that we just can't have. Of course, within the two-line program, we could, but... Okay, so I think he's done a really good job here of taking the original program and keeping all the logic and even the variables more or less intact, but shrinking it down to these 2 lines of code by using Boolean logic instead of if-thens to make it branchless. In C64 BASIC, if you have an if statement that fails, it immediately goes to the next line of code, which of course makes a 1-line version of this completely impossible, and even a 2-line would be difficult without this Boolean logic or branchless programming, as it might be called nowadays. Yeah, and that poking to location 0 that just happens once per run really doesn't seem to matter here. That input-output port handles the cassette drive and the memory mapping configuration about RAM or ROM being accessible, but obviously it doesn't matter too much here. It's not the actual control lines, it's just whether they're inputs or outputs. Now, Josip asked if it could be made shorter, and I think so. The one obvious thing is that these delta x and delta y variables here, dx and dy, could just be renamed with single letter variable names at the cost of some legibility or readability. And readability is not important in 1 or 2 line programs. But I think that would only save about 6 characters total, and that's not enough to get this scrunched down into just 1 logical line, which can have a maximum of 80 characters abbreviated on the C64. So I think we need to use a different approach that will get rid of some of these variables and logic, and maybe we can shrink it down enough to get it on 1 line. Okay, so something we can do to get some insight into what the program is doing is just get rid of these pokes here. So just got rid of the pokes that I actually put on the screen. And instead, we're just going to print XY for each step. The comma just makes it go to the next column. So if we run that, take a look at what the program is doing. You see it starts off at 0 for both X and Y and goes up. And if you look at the right column, which is Y, it peaked at 24, is now coming down to 23, 22, etc. On the left side, it's counted up to 39, and now it just started going down again, 38, 37, 36. And that's what happens is that, okay, there now Y is bottomed out 0 and is going back up again. And now here is the X, it just hit 0, and now it's going back up again. So you've got 2 lists of numbers bouncing between 0 and 39 for X, and 0 and 24 for Y. You can see they're independent of each other, but they're taking the same step each time, step of 1. So maybe that'll provide some insight into what's really happening. Rather than checking for collisions or whatever, really we've just got X and Y. They're like oscillators, each moving between a minimum value of 0 and their own maximum value of the screen width -1 and the screen height -1, as 39 and 24 respectively. So really you've got X going from 0 to 39, and then from 38 down to 1, and then it repeats again. That's what's happening. It's only at these extremes of 0 and 39 for a single step, but 38 through 1 are doubled, once on the way up and once on the way down. And y likewise just goes 0 to 24, and then 23 to 1, and then repeat. So can we make a branchless program that does this oscillation? Well, first you might think of using like a delta x, but to make it go positive, then negative, and so on. Well, really, you're just doing what the original program did. We need it to be simpler. We can't use that many variables. Can we get it down to just one variable, but still have that same up and down effect? So really, if you look at the x, 0 up to 39 is 40 unique positions. But going back down again is from 38 to 1, that's just 38 unique positions, which is 78. Or another way of looking at it is the extremes are only encountered once per cycle. 0 is encountered once, 39 once. So I put a print command in front of that. But the other 38 positions in the middle are encountered twice each, once on the way up and once on the way down. That's how you get that 78. And likewise for the y position, we have 1 plus 1 for the extremes of 0 and 24, and then the 23 positions in the middle are encountered both up and down for a total of 48 positions. So let's start with that. Can we count through 48 unique numbers, 0 through 47, based on a single variable? Yeah, well, that's actually pretty easy. If we had a modulo function, which some languages have, it would be really easy because we could just go y equals t mod, or in some languages it uses a percentage, 48, and then line 1, we could just print y, increment t, this is just our time step, and go to 0. And that would be our whole program, just endlessly counting from 0 through 47 and looping around. Unfortunately, we do not have that. This is going to generate a syntax error or something. Yep. C64 Basic just doesn't have that function. So we have to recreate it, but it's not that hard. Instead, y equals, you take the current t value and subtract the integer of t divided by 48. That is, how many whole 48s are there in t? This will give a fraction, but the int will truncate it. And then just multiply that by 48. And the remainder is the modulo we're looking for. Okay, so that's how you do a mod function in C64 Basic. Let's try running that now. What do we get? We start 0 and we go up. And here comes up 47. There, it wraps around 0. Counts up to 47. There we go again. Wrap back down to 0. And so on. And it will keep doing that more or less forever. I suppose if we let that run for years or months or something, t would eventually overflow. But we're not going to worry about that. This is for fun. Okay, so how does it help that we can now count from 0 to 47? What we want to do is count up to 24 and then bounce back down again. Well, if we just make one little adjustment here, if we subtract half of the period here, 48 minus 24, and we'll run it again and watch what happens now. It starts at minus 24, goes up to 0, and now it's going up to 1, all the way up to 24, but watch what happens here. 23 minus 24, but now it's going back down again. Well, it's going, okay, if you ignore the minus sign, it's actually doing exactly what we want. Now it's coming back to 1, back to 0. It's crossed over into positive now. But you see, we've got it going 3, 2, 1, 0, 1, 2, 3. Again, if you ignore the negative sign. Well, fortunately, there's a function for that called ABS, absolute value. Oh, we need to include that minus 24 inside the brackets. Okay, let's try running that. So there it is. It starts at 24 now. We might just have to live with that. But here it is. It's 24 coming down to 0. Now it's going back up again to 24. It peaked, and now it's going down again. So there you go. We've got our oscillator moving between those two values we need. Okay, so there's Y. And actually, we can get rid of one level of parentheses. They are not needed. And let's just add in basically exactly the same thing, a absolute value of, for X instead. And we're going to do a period of 78. As explained earlier, this is for the X position. It's 40 positions times 2 minus 2. And then we multiply it by 78. And we subtract half of it, 39. And closed bracket. And now here, instead of just printing Y, we're going to print X and Y. Okay, so it's just an extension, but now we're calculating both X and Y, but both based on that same T variable. So the program is almost exactly the same, except it has both X and Y calculations, and it's going to print both X and Y. Let's run it and see what happens. Okay, they both start their maximum value, and if you watch the right column, Y, there, it hit 0, and it's bouncing back up again. Look over at X. There, it hit 0, and it's bouncing back up again. There, Y peaked up at 24. It's coming down. And X is going to go up to 39. There, and back down again to 38, and so on. So there we go. So we have both of our numbers, both of our oscillators. They are not in sync. They're stepping at the same rate, but they're both independently oscillating for different ranges. Okay, so now instead of just printing those values, let's actually try and poke the ball to the screen using that calculation. Let's make some room for ourselves here. We're going to poke Z, 32. What's Z? Well, I'm borrowing that trick from Josip here using an uninitialized variable. That's terrible, but it seems to work. And now we're going to actually calculate our Z, 1024. Yeah, that's what we say in Canada, Z. Okay, and we're just calculating the screen position like we've already seen a few times today. And then we're going to poke Z, 81. That's that ball again. And then we're going to leave the rest of it with incrementing T and going to 0. Let's make sure that's okay. All right, can we run it? Does it work? There goes the ball. Looks good. Okay, so we've got it working. We've proved the idea, but it's still too long. So how can we shrink it down? Okay, instead of that existing line 0, let's do something that it doesn't get used very much. We're going to define a function, call it function A, for lack of a better name, and we're going to pass a B into it. And then we're basically just going to reconstruct those equations that we have in the existing line A, ABS T minus int T divided by B times B. So just wherever there's that constant up here, like the 78, that's going to be passed in as variable B. Now, how about that 39? Well, we can only pass in one variable, but that's okay because it's always going to just be half of B. So we're just going to subtract B divided by 2. Okay, so now we've defined this function. And now, in line 1, we're going to call it, instead of Y, we're going to call function A, one more space, and bracket, one more space, 48. Okay, so we're just going to call that function with a parameter of 48, which is the duty of the oscillator that we want. And likewise for x, we're just going to call that same function a, and with the duty for x, which is 78. Not sure duty is quite the right word here, but that's what I'm going to use. Okay, so that let us get rid of x and y altogether. Does that work? There it goes. And yeah, the ball is starting in the bottom right corner instead of the top left, but well, anyway, I'm okay with that. If you're not okay with it, you can try and fix that. Okay, so that seems to work. Okay, so final step. Are we finally there? Let's try and squeeze this onto one line of code. So I'm going to get rid of all the spaces and use every abbreviation that's possible. So I'm just retyping the above, but it's all going to go on line 0, no spaces. D, Shift E is the short form for definition, the abbreviation. And then function A, and then that equals the absolute value, which abbreviation A shift B, of t minus int t divided by b times b minus b divided by 2, and then a colon. And yeah, this function definition is going to run every time, but what can you do? Okay, now we're going to poke p shift O z comma 32 colon, and now we're going to set z equals 1024 plus function A 48, and we're going to multiply out by 40 plus function A 78 colon, or we're going to make it poke z comma 81, putting the ball back on the screen, t equals t plus 1 colon G shift O, and we got one space left and we don't even need to do line 0. Okay, line 0's in. Delete the old line 1. List the program, and there it is, all on one line. It's still valid because it was just one line when it was typed in. If you were to try and edit this, then you would have to re-abbreviate and retype in the end. But this is a valid one-line program, at least according to certain rules, or just, well, I say so. Okay, there it is. Does it work? Run. There it goes. Yay! One-line version of the bouncing ball. Okay. Oh, so that's where I'm going to leave it. I'm still not sure this is ideal. Maybe somebody can improve on this, and I welcome that. I don't make these videos just, to say, look, I am the best or anything. I realize that there's people who are better at this kind of thing than I am, and they may want to have a crack at this, see if they can further improve it. Some ways it could be improved if you can find the room. Yeah, if you really want the ball to start in the top left corner, you might want to do that. You might want to get rid, well, here, I'll list the program so it can actually be read. It still has that problem that Z is uninitialized, so it's poking at location 0. I don't really like that, but it doesn't seem to matter. So you might want to improve that. You might want to get that screen clear back in, but I don't know how you're going to fit that in. Don't bother trying to get those screen colors in, though. Those are terrible. Another problem is that by incrementing t here over and over again, that's a float variable. Eventually, that will start to get rounding errors and then overflow. So we cannot run this program for the rest of eternity, unfortunately, in case you wanted to. I did some math, and I think it's after about 55 fortnights, it'll start getting rounding errors due to the limits of floating point variables. And I'd also like to see the amount of flickering reduced. I think Josip's version, and actually my previous 2-line version, looked a bit better. And again, it's all about that length of time that the CPU spends between here, when you poke 32 to clear the ball, and all this calculation is done, and then we poke it back onto the screen again. This has actually gotten very lengthy here because it's calling this function twice. So could this be reordered? The thing is that you need to poke it at the old location, then you need to update the position and poke it at the new, and without using a second variable, which we don't have room for, like space for in the code. I don't know how to do that. Okay, so I think that's it for today. Thanks again to Josip Retro Bits for prompting this video. Maybe he'll have a follow-up video about this, or even if not, I'm sure he'll have other interesting videos about C64 programming, other topics, so check out his channel. Thanks to my patrons for their patient support. Thank you for watching, and we'll talk to you next time.